Okay, hello everybody. My name is Gage. Welcome to my lecture on helical antennas. First, I'll give you some physical examples of what these look like. You can see the helix right here. Going through all of these, they've got a fairly decent wide range of sizes, going from pretty small, handheldish, to very quite large. So let's look at some parameters of these things. They're largely described by their number of turns, the diameter of said turns, and the spacing in between those turns. Changing up those will give us a lot of different polarization, a lot of different radiation patterns, make our antenna more or less directive, more or less efficient as well. We can see here, the total length of it will be described as the number of turns times the spacing. The length of the loops in between each turn. If you imagine we take, like at this point, stretch it out along this axis to where this L naught here is a straight line. We'll get this kind of shape. Yeah. You can get this length pretty easily using this trig. That's your hypotenuse right there. This alpha is the angle between them. Total length of this wire will be the number of turns times the spacing. Sorry, not the spacing. L naught times L naught times the length of each of these bad boys. That alpha that I talked about earlier is called your pitch angle. Yeah. We'll move on here to our radiation patterns. The broadside or boring mode, the normal mode, it can be approximated by a small loop plus a dipole. It's got the same radiation pattern of a small loop or a dipole. It occurs whenever your number of turns here and the total length of the antenna, all of these, is a lot smaller than your wavelength. Basically, as you shrink it down really tinily, it'll pretty much just act like a dipole or a loop, depending on the spacing. This polarization here can also vary if you were to operate in normal mode. As this alpha, like I said, approaches 0 degrees. Oh yeah, let me go back. So the physical meaning, what's the physical meaning of this alpha? As you move it around. As you do that, your antenna will become more either squished as this goes to 0, and you'll get a wide, like one thick loop, or it'll be stretched all the way out as this goes to 90, and you'll just get a dipole. So you'd get your linear polarization in both of these cases here. Moving on, this is what we want to get to. This is the whole point of using helical antennas, is getting this end fire mode. It's what's really beneficial to us, also called axial mode. It's excited whenever your diameter of each of these loops and your spacing between them are large fractions of lambda. Benefit of operating in this mode as well, excuse me, your ability to achieve circular polarization whenever your ratio of your circumference and wavelength is between 3/4 and 4/3, or 0.75 and 1.25. Your spacing S will also have to be approximately 1/4 lambda, and that alpha I talked about earlier will have to be between 12 and 14 degrees in order to achieve this nice circular polarization. Operating in this end fire mode, it's got the added benefit of having larger bandwidth, and as you can see with your eyes, it's more directive than the old broadside mode. I want to talk about the effects of adding a ground plane. Practically, physically speaking, adding a ground plane as well. Not only is it nice to use end fire mode, those were these parameters. D's and S's were chosen appropriately in order to excite that mode for this antenna. Obviously, it didn't work. The number of turns here is 7. We tried tripling it to 21. It only increased our gain by a smidgen, and it didn't make it much more directive. But adding a ground plane, this is going to do that for you. You'll get almost thrice the amount of gain, and you'll become much more effective like we want with this ground plane. Speaking of, size of that thing will have to be at least lambda over 2 in order to have it produce the effect that you would want. Because your input resistance R will be almost purely resistive. It'll be about 140 times C over lambda. And that C over lambda is also probably going to... These cases, your half power beam width here, full node beam width, directivity, this axial ratio, which can be approximated whenever these 3 parameters are satisfied. Essentially, whenever you're using circular polarization, these equations will hold true. Only difference is number of turns will be greater than 3 there. So some usages and trade-offs of this helical antenna. Yeah, broadside mode, like I talked about, it's really not used. Might as well use the dipole at that point. It's got low bandwidth and poor radiation efficiency. The axial or end fire mode is high bandwidth, better radiation efficiency, highly modifiable polarization. Like we said, we can go from linear if you really want here, or we can get this circular, and in between those two as well, you'll get elliptical polarization should you desire. It's also much more much more directive, and it can operate in both ultra high and very high frequency ranges, 30 megahertz to several gigahertz. A couple disadvantages of the helical antenna: that input resistance gets a little funky. It's very sensitive to the feed construction, whether using a pin or a coaxial cable. The input resistance itself is usually between 100 and 200, kind of referring back to this equation, 140 times just about any fraction in this range. It's going to be between 100 and 200. We'd like that to be 50 ohms, so you'll have to implement some impedance matching techniques in order to achieve that. It's a little bit more engineering required. Also, maybe not got specific geometry, but as you shrink this thing down, it'll start to approximate like a dipole in a loop. This makes it a little bit harder to be efficient at smaller sizes. Like if you were trying to use it for a handheld device, you'd want to use a patch antenna. Just the dimensions of a helix, even at a very small size, it might be too large for your application. Other than that, it's about everything that I got. So if anybody has any questions, now's the time. I'll pause for a second, but if not, thank you all for joining, and good luck with your lectures.